Hi, this is my first YouTube video and I'm going to show you how to model ultrasonic transducer by using Abaqus CAE. I'm using version 6.10.2. So in general, ultrasonic transducer is a device which is used to convert electrical energy into mechanical energy. There are different configuration of ultrasonic transducers, and today I'm talking about a type which is called Langevin transducer or sandwich transducer. This type of transducer consists of different parts. The first part is the front mass, which is made from metal. The second part, which is a combination between electrode, which is made from usual from copper, and piezoelectric discs, which is a composite material that converts electrical energy into mechanical energy and created waves by exciting by harmonic excitation. And then the back mass, which is a metal as well, and the Prestress, which is used to combine or tie these parts all together during the operation. So in general, sonic transducer is excited by electrical potential energy, and then by vibrating on the same frequency of the excitation, the piezoelectric material will generate a mechanical wave which propagates through front and back mass. Usually the acoustic impedance of these parts is made so that most of the generated wave will propagate to the front mass, and also the front mass can be geometrically modified to magnify the amplitude of mechanical wave. Then the propagated wave will go through the front mass to the application. In this modeling, I've used the material which can be seen here. So for Prestress, bolt, and front mass, I've used titanium alloy. For the back mass, I've used steel, mild steel. For electrodes, I've used a copper. For piezoelectric materials disc, I've used B8, which I've got the specification from ceramic website. If you go through products and then piezoelectric materials, if you go down to the recommended downloads and then materials for power converters. So B8, Sonic's B8, I've used properties. And in general, piezoelectric manufacturing does not provide all the required parameters to define piezoelectric material in finite element codes such as Abaqus. Therefore, you have to go through these properties, and I've created a sheet which we can provide. I can use the provided data by the manufacturing to create the required data which is required in Abaqus. And in general, piezoelectric materials requires 3 different type of data to be defined, completely defined. It's required to define the elasticity, which is represent the mechanical part of this composite material. It's required to define the piezoelectricity, which represent the conversion from electrical to mechanical, and it's required to define the dielectrical properties, which define the electrical properties of the material. So piezoelectric materials is a combination between mechanical and electrical properties. In this sheet, you can get the properties from the manufacturing data for any type of piezoelectric materials, and by using these data as input data, you'll go through the calculation to get the output which is required by Abaqus. I'll try to upload this sheet with my video, but otherwise if you require more details about how did I create this sheet and other details about the dimension of these parts, how it's being calculated, you can go through this link. This is my PhD thesis, which can be accessed freely. And if we go back to the transducer, this transducer is designed to vibrate or resonate a longitudinal vibration at frequency around 20 kilohertz. In this video, I'm going to show you how to create your model and do the model analysis. And in the next video, I'm going to through the harmonic analysis, where we could apply a voltage across the piezoelectric material or piezoelectric disc and measure the mechanical response at any point, and particularly at the output surface, and also calculate the electrical impedance spectra of the transducer. So I've created a new project in Abaqus, and I'll start it to create these parts one by one. So from the part, we'll create first the front mass, which is modeled as a three-dimensional model in three-dimensional modeling space, deformable, solid, and I'll create it as a revolution type. The approximate size of the drawing sheet will be twice as the largest dimension of this part. So for this front mass, it's 70 millimeter length, so this will be 140 millimeter. I'm using the meter units in this drawing. So the base of the front mass will be exactly the same dimension as the piezoelectric disc, and this is the total length and the output surface. So as we have said before, the total length is 70 millimeter, the base is 19 millimeter in radius, and the height of the base is 50 millimeter. The output surface is 10 millimeter in radius, and it has a section which is used to hold the other parts to the front of the transducer, which is also 10. Now, as we have seen, the front mass is an exponential decay, and in order to create this profile, we have different approach, either by selecting number of points along the path and then join these points by using the spline feature. For simplicity, I've just select one point in the middle of transducer. I've created the location, I've measured the location of this point and the radius as well. So the point will start from here, and the height is 30 millimeter, and the radius is 12.5. Now I'll connect these 3 points to create the profile. I need to delete all what I've drawn. And if you delete it, the center line of rotating also will be deleted, so you can create it from here. Otherwise, it cannot be rotated around the center. Now I've completed the cross section of this the front mass. I'll just rotate it around the axis, and the angle of rotation is 360 degrees. Now I've created the first part, and before moving to the next part I need to check the type of construction which can be helped to mesh the front mass, and you can check which type you have by using the mesh control. So you can see there is different type of technology for meshing. The preferred one for model analysis is hexagonal and structured one. So in order to get any of these technique, you have to divide your geometry into different sections by using partitioning. So in partitioning, it just create a plane between mesh. It does not separate the model into parts. So I'll use these techniques to convert my structure to accept the structural meshing technique. So first I select point and normal. Select a point on the corner where started the exponential decay and select the central line, and you can see it's virtually separated into two parts, but in reality it's still one geometry. Again, I'll use it to split the base. So select a point, normal, and now I'll select all the model and using 3 point rather than point and normal. And again 3 points on the other way. We have seen the control is automatically changed to structured technique with hexagonal property. So this is for the front mass. The other part is the electrode, which I'll create through extrusion of solid, and the large dimension of these electrodes, which is shown in yellow, is the diameter or the radius, the diameter direction, which is 39, or we can see 38 millimeter, so we can use these as 80 millimeter radius. So the inner diameter of these electrodes is 16 millimeter, so the radius will be 8, and the outer is 38 millimeter and the radius is 19 millimeter. The thickness is 0.5 millimeter for these electrodes, and again I'll check which technique we can use, and by using the partitioning 3 points we can convert the sweep type or sweep technique into constructed technique. The third part, which is the piezoelectric disc, which I'll use the same as the electrodes extrusion to create this type, and it has exactly the same dimension of or of the electrode, except the thickness will be 5 millimeter rather than 0.5. So the inner will be 8 millimeter, the radius, and the outer is 19 millimeter. The thickness is 5 millimeters. Again, similar approach is used to convert this type of mesh technique. The third part is the back mass, which I'll use the extrusion to create it, and I'll use the same dimension or the same drawing layout which I used in piezoelectric and electrode parts. The inner diameter of the back mass is 12 millimeter, which is smaller than the piezoelectric material, and when we assemble the shape we will see why is that necessary. So the radius will be 6, and the outer will be the same as the piezoelectric material or disc, which is 19 millimeter radius. The length of the back mass is 36 millimeter. This dimension again is, you could find all the dimension and how did I calculate this dimension through this link, and the mesh technique can be changed from Swift to construction or constructed by creating a section or partitioning, sorry. At this point I need to define a set, which is a surface for the inner of the back mass, and we will see in the interaction module why do we need to create these surfaces. So for the back mass, I'll create a back mass surface, and we can select each surface because it's being partitioned into two. We can select each part individually. So I've select the first one, press shift and hold, and select the other. Or we could use by angle, so all the inner surface will be selected at once. Third part, which is the pre-stressing bolt. Which are created through the revolution, and the pre-stress bolt is coming through the back mass, the piezoelectric section, and fit on the front mass, and the total length is 70 millimeter. So I'll change the grid or the drawing sheet into 140 millimeter. I'll just draw a simple shape, then the dimension will give me exactly the required for, or the true shape or true cross section of that my bolt. So the bolt head is 0.1 or 10 millimeter, and the height 10 as well, while the washer, the diameter, the radius of the washer is 16 millimeter, and the thickness of the washer is 2 millimeter. The total length of the bolt, as we have seen before, is 70 millimeter, and the radius is 6 millimeter. These all dimensions are required to create the bolt and the cross section of the bolt, and now I'll just rotate it 360 degrees. Now doing the same by changing the mesh technique through creating different section, and the section or the partition is created on the point where the cross sectional is getting to be changed. So select points to create the section. For the washer, you have seen we have two different rings. The first ring is the bolt head met with the washer, and the second the bolt body met with the washer. So we can use the swept partition technique by selecting the shape and then selecting the circumferential of the meeting between the body and the washer, then select along the direction. Make sure the arrow will refer exactly where you are going to create the section. For we want to create a partition in the washer, so just leave it and create. Again, do the same from down side along, and is going up, so it's correct. Create the section, and finally we'll divide we'll partition the bolt into 4 quarters. So this will be divided into half, and other section to create the other half, and that's it. For the bolt, we need also to define 2 surfaces. The first surface where the bolt go through the back mass, and the second surface where the bolt go inside the front mass. And to do that, we need to use a feature, a datum point, and the datum point is offset from a point, so I'll go down to where how long the bolt will go through the front mass. I'm working on the Y direction on the negative side, and I'll select 10 to create the datum point. This is the first point. The second point, which is going from down and going up in Y, and it has the same length of the back mass, which is 36 millimeter. So it's come up to here. Now I'll use the section or the partition to create these surfaces. So I'll have surface here and surface in here. To create these surfaces, use surface, and the first surface will be bolt front mass surface. If I select by angle, then it will be select all the bolt body, which is I don't need. So I'll just change it to individual and select the surface part. So the first surface is this one, and now the second surface, which is bolt back mass surface, which is this one. Right. We have created the back mass, electrode, front mass, piezoelectric disc, and Prestress. And in front mass, I forgot to create a surface or create the section where the bolt go inside the front mass and fit. And this section will have the same dimension of the bolt, I mean the radial dimension. So by using create, cut, extrude, select the surface, so the radius will be 6 millimeter, and is going inside for 15 millimeters. Now I need also to define the inner surface of the front mass, so by using surface front mass surface, I can use the angle to select it at once. Okay, now we have created all the required parts. We need to define properties for material properties for these parts, and I'll start first with titanium, where the density is 4430, and the elasticity, or the Young modulus of elasticity, is 111.65 gigapascal. Sorry, this space. And the Poisson's ratio is 0.342. This is all the required properties for the titanium alloy. The next is steel, and the density 8000, while the Young modulus and Poisson's ratio are 184 Young modulus of elasticity and the Poisson's ratio 0.3. This is all that required for steel. Next, carbon. Where the density is 8942, and the Young modulus is 115 gigapascal, and the Poisson's ratio is 0.31. Next, the piezoelectric material. And for piezoelectric material, for the material I've used, the density is 7700, and we do have to define three other parameters. The first is the mechanical parameters, which is the elasticity, and instead of using isotropic, the piezoelectric material is considered as orthotropic material. For orthotropic material, we have number of parameters need to define, and again I've used the same names which is used by Abaqus to define these in the sheet. Make sure the same numbers you have using. So this two two three three. Now 3333. And finally 2323. So the elastic properties of piezoelectric materials have been defined, and now we are going to define the piezoelectric and dielectric properties from other. Go to electrical and then dielectric. Again, it's orthotropic material. So these dielectricity or dielectric properties. And the piezoelectric properties. At this point, we can define piezoelectric materials through two different types, strain or stress. I'll use stress definition, even you have both in the sheet. Make sure you are going through these properties correctly. I mean, match the property index number in the sheet with the required one in Abaqus. You could also define these material properties through subroutine, which requires a bit understanding of how to define the subroutine and assign these to the CIE. Once you have defined the properties of the piezoceramic, you could add these properties into material library, so you don't need to do it every time. You can just copy it easily from the material library. Now I've defined all the required parameters for piezoelectric, dielectric, elastic, and density properties of material of the piezoceramic. Now all the materials have been defined. We need to define the sections as well. So first define the titanium. Section. It's solid and homogeneous. And then the steel section. Same. Copper section. And finally piezoelectric section. Now these sections need to be assigned to each part we have created previously. So for the back mass, which we have seen, we have said is steel, made from steel, and for electrodes, which is copper, front mass, which is titanium, piezoelectric disc. And because piezoelectric disc is an orthotropic material, it's required to define the preferred or axisymmetric axis. And in piezoceramic material, we call this as the pole direction, where the material will be excited and will be respond at this direction. In this model, I'm using the Z direction or direction number 3 as the pole direction. So first we need to create a datum coordinate system. I'll call it just datum 1, and the origin of this datum will be 0, 0. So it's the back surface of this disk, and we need to select a point on the x-axis, and finally a point on the xy plane, which I'll select this point. Now we have created the datum coordinate system. We can use the assign material orientation. So it's required the datum axis, and here we have defined the coordinate system as I've said before, and we have used the additional rotation direction as x, and the stacking direction, which is the isoparametric direction 3, bottom to top. So just press OK. Now all the parts have been created, all the material have been defined, sections, and we have assigned the section to the parts. We are going to the next step, which is the assembly step. Now I'll select first the back mass to be in the origin where the axis will be created, and all the parts will come to assign through the back mass. Make sure you have select auto offset from other instance, so just press apply. We need one back mass, we need one Prestress bolt, and we need 3 electrodes. So 1, 2, 3, and 2 piezoelectric discs, and finally the front mass, and press OK. Now by using the constraint, we have defined face to face. So I'll define the movable plane face of the bolt, and I require this face to match or the back mass, the face of the back mass. Make sure the row be on the same direction, so both refer to the back, and the space between will be 0. Then use coaxial, select the movable part first and then select the fixed part. Make sure the arrow again on this refer to the same direction, and that's it. Now do the same for the electrodes. I'll select the back surface of the first electrode, which can constrain or can attach to the front face of the back mass. Make sure the arrow refer to the same direction and the distance is 0. Coaxial again, select the movable part and the fixed part, the arrows in the same direction, and so on. Then I'll bring the first piezoelectric disc, select the back face to touch the front face of the electrode, change the direction of the arrow, distance is 0, and then use coaxial to bring it to the right position. Again, do the same for other electrodes. And the other piezoelectric disc. Finally, for piezoelectric stack, fuse the electrode on the front face of the piezoelectric disc, and using the coaxial to bring it for the front mass again. This will be touch the electrode surface. Make sure both arrows on the same direction and the distance is 0, and again coaxial between the back mass and the front mass, and that's it. Now all parts are coming together. However, we need to define interaction between parts, otherwise it cannot be working properly. Even if you bring these parts close to each other, they can't see each other unless you define the interaction. And to do the interaction, or to define properties between the interaction, I'll use the general contact, which I've seen the best method to do, and there is another methods such as define the surfaces and define the properties between surfaces, but I've seen the best way to do that is using general contact standard, because we are doing a standard modeling. So press continue, and at this point it's automatically select all the surfaces, contact surfaces, to be defined. However, in this model we need to exclude one surface, which is the surface between the bolt and the front mass. I can show you the surface by removing some parts. So this is the front side of the bolt, and this is the back side of the front mass. I need to define another interaction between these surfaces, which is called a tie. In the tie, you could define these, or you could define the teething or the tight properties between these two surfaces. Therefore, if we go back to them, we can exclude these two surfaces from the interaction, the general contact interaction. So go to this window, select first the front mass. We have already defined the surface and the prestress and bolt, the prestress bolt and front mass surface. So these has been now have been excluded from the definition of the interaction. Now, in order to define the contact properties, we need to assign the global property. So right click, create, and the first will be general contact. I'm using contact, and at this step I'm using tangential behavior to be penalty, and I've used the friction as 0.5, while for normal I've just used the default which is used by Abaqus. So hard contact, default, allow separation. I'll just check this off so I don't need any separation after they've come to contact each other. Okay, I need to create another type of properties which is between the back mass and the bolt. So the bolt body and the back mass need to define as frictionless rather than penalty. So in order to do that, create frictionless contact, and in tangential I'll leave it as a default by Abaqus, while the normal will be the same hard contact, but do not allow any separation after contact. Now for the general contact of all parts, I'll create just the general contact. While for the back mass and the bolt body, I'll just assign the back mass, bolt body and the back mass, and frictionless contact, and that's it. Now we have defined the interaction for all parts. We have assigned different contact between the back mass and the bolt. We just need to assign the contact properties for the surfaces we have excluded, which is the front of the bolt and the front mass. So go to constraint and select tie and constraint bolt and front mass. I'll leave this tie. So I'll select from surfaces because I've already selected the surfaces, and the master surface will be the front mass surface. You could highlight it to see it, and the slave will be the pre-stressing bolt and front mass. Sorry, just repeat it. So side constraint bolt and front mass. So the master surface will be the front mass, the front mass surface, while the slave will be the pre-stress bolt front mass surface. Now I'll just leave all the default specified by Abaqus. Now we have, as a quick review, have defined the parts, materials, section. We have assembled the shape. We have defined the contact. Now we are going to create the analysis step, and the first step I will create is the static step to apply pre-stress, where in reality the bolt is applying pre-stress on all these parts when it's tight, and this pre-stress will affect on the properties of the piezoelectric material we have defined before. So in reality, as piezoelectric material, a composite material, the pre-stress will affect the elasticity, piezoelectricity, and dielectricity. However, in Abaqus, only the elasticity effect will be considered, and this is one of the limitations in modeling of piezoelectric material in Abaqus. So first I'll create a general step, general static step to apply the pre-stress. I'll select static general from general, and the most important, I have to sign on the non-linear geometries, otherwise Abaqus will not consider the pre-stressing effect on the model. Now for increment, I've selected time period is 1, so increment I'll just divide it into 10. The maximum will be 0.2. So these numbers I've assigned here, so the step will be divided, will be started from 0.1, and by default which is automatically to select step, and it cannot, the step cannot being over 0.2 reaching up to 1 to apply the load. And this step will applying pre-stress load, so go to loads and select general static step and pre-stressing load, and you could find a bolt load. So continue. Now we want to assign this to a surface, and to do that we can use view assembly display options, and you can see all the instance we have created is ticked, so set off and just show me the bolt. Now we need to select a surface to apply this load, and the surface for at this point is the surface, the inner surface of the cut, so I'll just remove these to select this surface to apply the pre-stressing load. So now choose the side for the shell or internal surface, and you have two color, brown or purple. I'll select the brown one. Well, you can see it, the side, so it's brown, and select the axis where the force will be act, so the surface, and the force I've calculated is 33 kilonewton. Again, you could find all these calculation in the link I've provided at the beginning of the video. Now bring all instance on and just leave this window in case you need it. Now we have assigned the load for the first step. I'm going to create the second step, which is the model analysis step. And the procedure type will be linear interpretation, and select the frequency. As I've said before, this transducer is designed to work on resonate at frequency around 20 kHz, so I'll just select the minimum to be 10 kHz and the maximum will be 30 kHz. So we could pick the resonance frequency and the resonance frequency for the operating mode, and the mode which is the neighboring modes as well. Now we need to define the mesh, as we haven't meshed the model, and there is two ways to define mesh. We can assign the mesh for each part, or what I prefer to convert all these parts to be independent, so it can be meshed through the assembly model. So just select make independent, and now going to mesh. Now I'll select element type, select all the model, and use 3D stress quadratic reduce integration. And for piezoelectric disc, we have to select another type of element, as these parts have additional degree of freedom, which is the electrical degree of freedom. So just set all off and just select the piezoelectric disc. Now from the mesh element type, go down to select piezoelectric element quadratic reduced integration as well. Now set all on, and then we need to assign the element size. So from seeds instant, select all. At this point you can select different type of size and then run your model to compare between the result you have got with the element size. This is what they've called the mesh convergence test. In this model I've just used 0.002 and then mesh the part, I select all the parts and generate a type constraint across the incompatible interfaces. Now the model has been meshed. Finally, we need to assign a boundary condition for piezoelectric material, and at this stage piezoelectric materials can be assigned to different types based on what frequency you require to resonate. If you are required to resonate at resonance frequency, then you have to define the boundary condition for electrical on both sides of piezoelectric material. Otherwise, if you want to operate your transducer at anti-resonance frequency, you need to define one side of piezoelectric, the boundary condition of piezoelectric disc, and this all has been cleared in the link I've showed before. So this transducer is designed to operate at resonance frequency, therefore both sides of piezoelectric disc need to be defined boundary condition, electrical boundary condition. So again, I'll just select the piezoelectric here and I'll select the first one, boundary condition, other, select electrical potential, continue, select the first surface, and sorry, just go back. I'll just create it from the initial state. So other, electrical potential, continue, select the first cell, again for the second surface, continue, now I'll select the second one, second disk, and then finally the back surface of the second disk, and now on all the transducer. Now to summarize what we have did, we have created the required parts, we have created the material, we have assigned material to section and then assigned the section to parts, we have assembled our model, and we have created interaction between these surfaces where we excluded two surfaces. The first surface is internally excluded, which is the bolt and the back mass, and the second one, which is the constraint, the bolt and the front mass. Then we have created the first step, which is a general static step to apply the prestress, and we have assigned the load, required load. Then we have created the second step, model analysis step, and also we have defined the boundary condition, electrical boundary condition of the piezoelectric disc. Now I'll create the job, model analysis, no, sorry, it does not accept any space, so small analysis, and I'll just check if the input file is complete to be run, and I'm usually run these files or jobs on a server, because if it's run on a computer PC, it will take long time. You could also monitor the checking and check if you have a warning message. Most of these warning messages does not affect your result or your analysis. However, some of these may affect, so you have to check them to make sure everything is fine. I'll just close this window, we don't need it anymore. And so we have elements missed property. If we go back, we can check which part does not assign correctly. So if it's green, or it's correctly assigned, so this part as well. Front mass is correct. Piezoelectric disc is correct. The Prestress bolt, we forgot to assign the section for it, so double click on assign, select the bolt, and then titanium section. For that reason, it's important to check your input file before you submit the job. Otherwise, you submit and keep waiting, and these mistakes can just give you an error and stop the analysis. While this is running, I'll show you what we are going to do in the next video. I'm going to show you how to assign, or how to do a harmonic analysis for the same transducer, and how to calculate the output response for different excitation, and also most importantly the electrical impedance spectra. How can we calculate it from this analysis? Also, we'll learn how to assign damping to the harmonic analysis step, which is important to get an accurate result. Although the checking could take time to be completed, I would strongly recommend to go through, check your file before you run it on the server. As you can see, the required RAM is also increased because of the size of the file, and it's completely, so it can be run now successfully. I'll show you the result on the next video for the model analysis, and then continue to the harmonic analysis. Thank you for listening. Hope you enjoyed and learned something from this video.